continuing estimation of autocorrelations of an AR2 model, we can make use of the concept of difference equations, very similar to differential equations, but we just deal with discrete series in this case. So if we recall, an AR2 model is simply xt minus v1, xt minus 1 minus v2, xt minus 2, and that equals to a sub t, where a sub t is noise. And we can write the series using the backwards operator. And here we have xt in common, so xt would come out. We have 1 minus v1b minus v2b squared equals at. I could write that expression that I see here as phi b, and that phi b is the characteristic polynomial of the AR2 model. So if we have a characteristic polynomial, then we can factor the characteristic polynomial and find autocorrelations using phi1 and phi2. So we typically have roots of a polynomial to be real or complex. And in a simple case, when we have a quadratic equation, 1 minus v1b minus v2b squared, it is, we could find the coefficients using the quadratic formula. But when things are a bit more complicated, then we would have to look for other ways to find the roots of the characteristic polynomial. So there is this entire concept of a difference equation. The difference equation, I'm not sure if you've taken differential equations. As I mentioned earlier, difference equation is just a discretized version of differential equations. So in our case, we know that the autocorrelation function so rho k is related to the model coefficients. So we can have, or we have, rho k is equal to phi1 rho k minus 1 plus phi2 rho k minus 2 plus phi3 rho k minus 3 plus dot 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 phi p rho k minus p. Now I am generalizing this to an ARP model, but if it is an AR2 model, we'd have only the first two terms here. So this is the standard autocorrelation function of an ARP model, and we would want to find the solution to this rho k, or rho k expressed using values of the characteristic polynomial phi of b. How do we go about doing this? It might look scary, but it is not. So rho k is the sum of I equals 1 to v, sum j equals 1 to mi minus 1, and we have Cij, k raised j, and ri raised negative k. So let's break this down. So v is the number of roots for the characteristic polynomial, and mi is the multiplicity of the ith root. Cij are constants. So let's consider an example. We sort of have to go for something simple. Let's say consider a quadratic equation x squared plus 3x plus 2 equals 0. Now, this particular equation has two roots. If we factor, we could write this as x plus 1 times x plus 2 equals 0. So the roots are -1 and -2. You can say that these roots are unique in the sense the roots do not repeat. So in our case, v here would be 2, going back to the formula, and the multiplicity m1 for the first root is 1. In other words, it doesn't repeat. The multiplicity for the second root is also 1 because it does not repeat. So if we have a simple quadratic equation and you can find its roots, and I can find v and the corresponding multiplicities just by looking at the factors. So taking this one step further, let's consider as an example, x plus 3 cubed times x plus 1 times x plus 2 equals 0. This is a fifth degree polynomial. And does it have roots? It does. So first let's look at x plus 3 cubed. And if you set that equal to 0, x would equal to -3. So this is one root, but it repeats 3 times. The reason for that is the power 3. So in this case, we have m1 equals 3. And the next root that we have is x plus 1 equals 0, which would imply x is -1. m2 is simply 1. And x plus 2 equals 0, which would imply x is equal to -2. m3 is 1. So we have 3 roots . So we have three roots with multiplicities m1 equals 3, m2 equals 1, and m3 equal to 1. So if I go back to the notation that I'm using here, so for our case with the autocorrelations, if we look at our notation, v would equal to 3 because we have three roots, and m1 would equal 3, m2 would be 1, and m3 would also equal to 1. Now, let me quickly do a simple example with the autocorrelation form itself. Suppose the roots of the characteristic polynomial are 1.5 and 2.4, and we want to find row 3. So how do we go about doing this? So first, how many roots do we have? V is 2. We have 2 distinct roots. The multiplicity for the first root is 1. Multiplicity for the second root is also 1. And row k is given by this formula written previously. So the sum would simply become 1 to 2, 0, 0 to mi minus 1, and Cij Ri raised negative k, k raised j. And when we plug in the values of I, we would have the inner sum going away because the multiplicity m1 and m2 are just 1. And here, no matter what value of I we plug in, 1 minus 1 would be 0, so the sum would start at 0, end at 0, so there is no sum at all. In the sense, j here would simply be 0, and k raised 0 is actually 1. So this would reduce to Cij Ri raised negative k. So if we plug in the value of the roots, and I'm going to get rid of the j part of the ij because the sum just dropped itself. So we would end up having c1, the first root, raised negative k, plus c2, the second root, raised negative k. So we'll have c1, the value of the first root is 1.5 raised negative k, plus c2, 2.4, raised negative k. If we have the values of the constants c1 and c2, we can simply plug in the value of k and find the autocorrelation function. So in this case, row 3 would be equal to c1 1.5 raised negative 3 plus c2 2.4 raised negative 3. all we have to do is we have to find the values of the coefficients C1 and C2, which we can find if we have observed samples. So another example on this. So here, suppose the roots of the characteristic polynomial in an AR3 model are 1.5, 2.7, and 2.7. We have to find an expression for row k. So we have two roots. So the first root is 1.5. The second root is 2.7. But 2.7 repeats twice. In other words, it has a multiplicity of 2. So in total, we end up having 3 roots. So V in our case is 2, M1 is 1, and M2 is 2. So going back to our sum, row K would be the sum I equals 1 to V, sum J equals 0 to Mi minus 1, and Cij, K raised J, and Ri raised negative K. So I equals 1 to 2, J here 0 to Mi minus 1, Cij, K raised J, Ri raised negative K. So when I is 1, J is 0 to M1 minus 1. I is 1, so I'm going to plug in 1, J, K raised J, R1 raised negative K. Next step, we have I is 2. If I is 2, Mi becomes M2 minus 1, and I'll have C2J, K raised J, and R2 raised negative K. We have the values of M1 and M2 in the problem, so this would become sum J equals 0 to 1 minus 1, C1J, K raised J, R1 raised negative K. Over here, sum J equals 0 to 2 minus 1, C2J, K raised J, R2 raised negative K. So J would go from 0 to 0, which would mean J is 0, so we'll have C1 0, K raised 0, R1 raised negative K. Over here, the sum, it goes from 0 to 1. C2J, K raised J, R2 raised negative K. So C1, 0, any number raised to the power of 0 is 1. So we end up having R1 raised negative K. The second part, when J is 0, I get C2, 0, K raised 0, R2 raised negative K. When J is 1, I would have C2, 1, K raised 1, R2 raised negative K. Therefore, we'd end up having C1, 0, R1 raised negative K, C2, 0, R2 raised negative K, plus C2, 1, k times r2 raised negative k. We know the values of r1 and r2, it is given in the problem, so this would imply rho k is c10, 1.5 raised negative k, c20, 2.7 raised negative k, plus c21, k times 2.7 raised negative k. It might seem like complicated, but if you can understand the summation here properly, then, or correctly, then you should be able to find the autocorrelation function. So understanding the sum is very, very crucial to getting a problem of this sort completed correctly.